Oh, I give you control, didn't I? Okay, good. Okay, so the left cosets are H and let's say 1, 3, H. Which is the same thing as 1, 3, and 2, 3, H, which is 2, 3. Now, what the permutation representation is notice that the left action, so S3 acts on the set H 1, 3, H, and 2, 3, H. Left multiplication, right? So for example, notice that so let me conveniently number these cosets, say, let's call them so if you look at, let me pick an element. 1, 2, in S3. What is this action on A? Well, 1, 2, H equals H. And if you look at 1, 2, 1, 3, H, this is because of 1, 2, H, which I can, good thing I listed them over here. That should be the same as 2, 3, H. And if you look at 1, 2, 2, 3, H, this is 1, 2, 3, which is 1, 3, H. So in the permutation representation, this should take the element 1, 2 to the permutation right, because it leaves what I call 1 here alone and it flips the other two. If you look at, for example, 1, 3, 2, how does this act on A? We'll measure how it acts on A. I get 1, 3, 2 H is 2, 3 H. And I get 1, 3, 2, 1, 3, which is 1, 2, 1, so which is H. And 1, 3, 2, 2, 3 H is which. So what this one does is permutation representation. It should take 1, 3, 2, and it should do this. So what is this? This is like H goes to 2, 3H, and 2, 3H goes to 1, 3H. The 1, 3H better go off the page. Yeah, and it does. So this is 1, 3, 2. Notice these are permutations of the original letters, and these are permutations of this, the way I've listed.
Oh, what's page?
Page is the homomorphism that takes the group into the permutations of the set. Right. So your input is an element of the group, and your output in yellow is a permutation of the set. That makes sense. Okay, and I wanted to talk about, I will let you all kind of go through the proof of that last theorem, but I did want to go through the proof of, in fact, the one that you talked about. So, let me kind of get you up to speed here. Action. So G acts on set of what post this example is sort of a good one for this, because this is exactly what we did here. What I refer to in the theorem as passive H is the homomorphism, whose input is elements of the group, in this case S3, and his output is permutations of the set. So I want to prove the statement here. The kernel of this action is the intersection. It's just a set of all constants H, or the intersection of all constants H. And this is called kernel of the action. And the largest normal segment of G. Notice there's always a normal subgroup of G contained in H. You might have to be desperate to go all the way down to the identity, but it's in there, right? So for a particular, if G is a simple group and H is a non-trivial subgroup of it, this has to be the identity. So why is this true? The kernel of the action and of course, I mean left multiplication on the cosets, is precisely the set. So this is going to be just me massaging the set. G and G such that G acting on any X H is in fact still X H. The kernel of the action is everything in G, and when it acts on any of these left cosets that we go up. Okay. Set of G and G. So there's not much to this step here. I'll just replace G circle X with what it is. My action is just translation of this. This is the set of G and G such that X, G, X inverse G, X, H. Everybody okay with that? Now, what does it mean for X inverse GX to be an H? Well, it just means that this blob here That has to be an H. So this is set G and G such that and I should be saying for all X and G all the way down. There. So let me massage this again. This is a set of G and G such that I'm going to multiply this on the right by X, left by X inverse. Which is, this is a set of everything in G that's contained in every single one of these conjugates. Which, okay, so there's the kernel of the action. Now, let me give you a couple of points of view on this business about normality.
That's what the accent.
What's that?
In the last class,
Yeah.
it's accent.
What's that?
The simple.
Oh, yes. I didn't see what you talked about. Yes, you're absolutely right. Better, much better. Thank you. Okay, so let me make a statement about normality. Notice. Okay, so there we go. It's normal because it's actually the kernel of permutation representation. If you don't like that, this is kind of a neat thing. One of the corollaries is you can actually directly show that if you have any subgroup of group G and you look at all of its conjugates and intersected, it's always a normal subgroup. See if you can show this directly. It's a little bit annoying just because you got to do a little bookkeeping, but it's not too bad. So this is always a normal subgroup. And I did say it's what the largest normal subgroup that's contained in H. Right. Let me focus down. Clearly, and also, no. Right. So we've shown that this is normal. It's certainly contained in H because one of these conjugates is when X is the identity, right? So it's certainly contained. Yeah. A is another subgroup. Such that number one, K is normal, and number two, K is contained in A. Then K here. And because the fact that K is normal, and that well. So in particular, K must be contained in there because it's contained in every single one of these conjugates, so it's contained in there. Okay. Any questions on that? Okay, so here's an example, and this might help you with your homework if you haven't slotted through that yet. So here we'll take to answer this question here. Uh, 20, 25. Let me point out, just for giggles, that there is a subgroup order 20 in S5. And in fact, there is a transitive subgroup of S5. By transitive, what I mean is, it's a subgroup of S5, and given any two numbers between 1 and 5, 2 and 3, 3 and 5, 1 and 4, whatever, there's a permutation in that subgroup order 20 that takes I to J. Right? But as it turns out, there's no subgroup order 20 in that 5. Let's see if we can get to the bottom of this. I mean, you know, A5's got 60 elements. That's a lot of possible subgroups. Nobody wants to slide through that. And here, I'm going to do conjugation action. You can do left coset action too. See if you can work through the example like this. Let's let G act on. Or let A5. H. By conjugation. So in other words, G acting on conjugate of H. So there's our action, right? And the first, so basically what I have is I look at the subgroup 420 and I look at all its conjugates. And I list them. Certainly there's only finitely many, because there's only finitely many subgroups in group 460. By the way, how many conjugates could there be? My notation, what G equal A5, so that I don't have to go with subscript. What is the stabilizer? This is the set G and G. So it's the G H inverse set. What are the possibilities for the order of stabilizer? Let me point out that the stabilizer must contain all of H, because certainly if G is in H, then this is certainly the case, correct? So the stabilizer contains all of that, but it's also contained in a group of order 60. So what are the possible orders of stabilizer? Right, this is order 20, and this is order 60. So actually, it's got to satisfy two things. It's got to be a multiple of 20, and it's got to divide 60. Right? So the order must be either 20 or 60. Everybody agree with me? Can you eliminate this? Mean for GH, the order of GH is 60. What's that?
H needs to be a quarter 60.
Well, you're actually close. What it means is it means everything in the group stabilizes H. Everything. What does that mean?
So just normal.
It means H is normal. But this is a contradiction. Now, I don't know whether or not there's a subgroup order 20, but what I do know is the only normal subgroups of S5, I'm sorry, this is even better, it's A5, right? I know that A5 is simple, I'll prove this, right? So, all right, so this is right out. What's that?
Or is GH?
Yeah, this is stabilizer of H. So this is the set of everything when you conjugate H.
It's a subgroup of two.
Right.
Not a subgroup of A5. Wait, no, which is A.
Right, right. And so H is our subgroup order 20. And so if GH is all of G, it's all of A5, that means everything in A5 conjugates H and leaves it alone, which means that H is a normal subgroup of A5 of order 20, and that's impossible. The only normal subgroups of A5 are order 60 and 1.
Yeah, because of H is order. I was thinking of GH being, and it's order 60. I'm like, well, of course it's normal because it's the order of the group.
Right. GH is the stabilizer. So we conclude the stabilizer of H is just H itself, right? Because it has to be one of these endpoints, and it can't be this one, so it's got to be H. So, next question. How many conjugates are there? How many distinct conjugates do we have? So, this was my favorite thing. The length of the orbit is the index of the stabilizer. So, there's three conjugates. I agree with you. So, yes, you did. The homework. So this is partially from the notes and partially from your homework. P from G, say 5, onto permutations of the conjugates of This is the permutation representation we've been talking about. Input your element of A5, see how it acts on the three conjugates, and that gives you this sort of thing. Now, let me ask you this. We've now got a homomorphism from A5 into S3. Can this homomorphism possibly be 1-to-1? No way. Right? Because A5 is too big. Order of A5 is 60, which is greater than 6, which is the order of S3. So C is not 1-to-1. So the kernel of B is A5. Why is that? That is correct. A5 is simple. You've got two normal subgroups, the identity, which the kernel of P can't be, and the whole shebang, which is all you got left. So P is trivial. Therefore, for all G in A5, P of G is identity permutation. Somebody tell me what's wrong with that? There's something very wrong with that. Remember, how do we get what P of G is? We read what G does to the conjugates of H. In particular, GH, G inverse should equal H for all G and G. Because the element H should always go to itself. And this, so H in A5 is normal of order 20. And there's so it is impossible for A5 to have a subgroup of order 20. This, I hope, gives you a little bit of a taste of the power of looking at these, looking at things from this point of view. Okay. Any questions so far? Okay, so let's, here's some more on action. I'm going to give, this is sort of a preliminary class equation. How many of y'all, I'm sure you've all seen the class equation at some point, maybe in the first abstract algebra course. Maybe you don't remember. Does that ring a bell? The buzzword class equation? Well, we'll see it again. I'm going to give a preliminary kind of look at it, and then I'll write sort of formally what it is that you'll see it book. So let G be a finite group in X and G. And A, the number of elements in the consequency class of X. And let me refresh your memory about what I mean by that. What is the conjugacy class? It's the set of all conjugates of X. So this is the set of GX, G inverse as G range. So not just X, but all its conjugates. Notice that this is an orbit. This is the orbit of X under conjugation action. So it's G acts on itself by conjugation. G circle X is the conjugate of X. But this is just the orbit of G. And this number of elements is this. It's the index of the centralizer in G of X. And notice this, of course, must divide G. And B, if X1, X2, X bar are the consequences classes, are the conjugacy classes in G, what do I mean by that? Well, for example, X bar is a set. It's a set of everything that's conjugate to X. And so what I can do is start with X. Look at all its conjugates. Take those out. They're in the class by themselves. If there's anything left, if there's nothing left over, then I've sucked up all of G. If not, there's something else left over, X1. Look at all the conjugates of X1. Pull that out. If there's anything left over, call it X2, we conjugates that. And this eventually must exhaust since G is a finite group. There is an element in particular that has an orbit of length 1 in its conjugacy class. Anybody name that element? The identity, right? Because notice the orbit of the identity is just the identity. Because generalize that statement. There are other elements, perhaps. Any element in the center has only itself in its conjugacy class, right? But we'll collect all these, collect all the conjugacy classes, then the order of G I is 1 to N, central measure. And last we see, if K is a subgroup of G, then the number of subgroups of G conjugate K the number of subgroups of G conjugate K is given by the index this equation is called the class equation right here. This is very important. I'm going to write the class equation another way that's probably more familiar that many of you may have seen before. But here I'll do it. Generality. Bring this more general form. Okay, let's do it this time. So we start at it. Okay, A should be pretty easy actually. So let G act on itself about computation. So G acts on X, G we've seen that this is a bona fide action. If X is in G, then orbit of X is the set of Gx G inverse. Right? Which is precisely the set of conjugates. Notice that X itself is in X. And the orbit of X is the index of stabilizer. So it remains to show that it remains to show that these two things are equal. Stabilizer of X is precisely centralizer. Centralizer of X is G. I'll show a subset this way. Let G X and G acting on X, this is G X G inverse. X. Therefore, this means that Gx equals X to G, and so G is in the centralizer of G. Because G commutes with X. On the other hand, I claim that the centralizer G of X is in the stabilizer. So that establishes part A. And notice I did make the remark, so let me make a note. Proof that the order of G is and so this thing must provide the order of G. Notice I do need the G's proof here. This is the index centralizer. Remember, the centralizer G is the back proof. I'm sorry, the centralizer. Yes. Yeah, sorry, centralizer. I'm saying that wrong. Okay, let's tackle the class equation. Okay, notice that set of equivalent classes and these are the orbits. Under this action. Here's that part two. Right, this is true for any equivalence relation. When we prove that, of course, in each proof action equivalence relation, the set of equivalence classes forms this, and our equivalence classes are conjugate classes because it's conjugation action. Notice that G is equal to the equivalence class of X1 union the equivalence class of X2. The equivalence class of Xn. I put those dots over the union to just emphasize the fact that this is a disjoint union. If you remember, two equivalence classes are either exactly the same or they have no intersection, an empty intersection. Notice that my list is finite, and that depends on the fact that G is a finite group, right? Since this is a disjoint union, that means that G is the sum of and this is our previous G sum. I think it would be good for me to leave an exercise to the last one. The difference is now instead of looking at conjugates of elements, you're looking at conjugates of subgroups, in this case, the subgroup K. And basically, the analog of the centralizer of an element is the normalizer of the subgroup. Okay. Any questions? Let me give you the next theorem. This was kind of the same. Any questions? By the way? Okay, theorem. Let G be a group. Then there is a group monomorphism so 1-to-1 from G into where a okay, so this is actually important. This is a really kind of cool theorem. What it says is if G is any group, then there is a 1-to-1 group homomorphism from G into some permutation group on a set. So in other words, what that means, since this is 1-to-1, is any group that you could ever encounter, you can think of as a subgroup of a group of permutations. This means maybe that if you understood all groups of permutations on any set, then you understand all groups, because no matter what wacky group I can come up with, I can realize it as a group of permutations, right? This is probably maybe starting to get a little bit obvious when we start looking at permutation representations, right? Let the group act on itself and it gives a permutation into the set that is the group itself. So every G and I'll up the voltage a little bit for you. Yeah, your G is in G Now, let me point out that if you want to do things generally, then this is pretty much best possible, right? Because there are bad examples out there. However, in practice, if I have a group border N, putting it inside Sn is ridiculously big, right? So for example, let me see. When I say it might be too big, like, for a particular group, you might be able to find a smaller SN, but let me give you an silly example. Consider as 5. Right? Theorem says that G is a subgroup S 1, right? Which is really kind of ridiculous because things are freaking permutation proof in the first place, right? Why would you go put it inside this thing, which is totally out of control, right? But I take a little comfort in the fact that you can do it. And of course, S5 is a group of order 120, and it's very efficient, right? So let me give you an example. 5 is a subgroup of S10. That's what the theorem says, because D5 has 10 elements in it, right? But also, D5 is contained in S5. If you represent D5 generally by 1, 2, 3, 4, 5, and 2, 5. So here we did better than S10 by putting it in S5, right? Okay, any questions on that? As cool as this theorem is, I can prove this very quickly. Because we've kind of done a lot of the groundwork for this. So let's do the proof here. We're going to let G act on itself by left translation. So again, of course, one of my favorite, there's a lot of utility of G acting on itself and also G acting on cosets, subgroups. But of course, what I mean by this is G acts on X by multiply. Notice this is an action again, E times X is X, and it's associative because of the associativity of G. This induces a homomorphism. Representation induces the homomorphism, which we call pi from G into S. Okay, so what do I mean by that? Remember, this is like all permutation representation work. My input is an element of G, and you see how G acts on the elements of G. This gives you a permutation. Here, G is just considered to be the naked set, right? Not just really a group. You just look at the permutations of the elements of the group induced by this. And so, let's suppose, so this is a homomorphism. And all I have to do is prove it's 1-to-1. Suppose so what that means is pi G is identity permutation. That is to say, pi G which is equivalent to saying that G acting on X, G is X for all X, which implies that G is the identity. So, is and we're done. The second statement about being able to embed a group order G into, or a group G of order N into SN follows basically from proof, because if G has N elements, then this is SN. Okay, this is a good place for us to stop for the day. Any questions? Okay, next time I will give you a more, maybe you've seen a familiar way to write the class equation, and then we'll move on to do some more stuff with finite groups. So it's getting exciting. All right, questions? Don't forget, I've got to be gone shortly after my second class today. If this is screwing up your life, come talk to me now. We'll work something out. Other than that, I will see you guys on Friday. Any questions out there? Okay, thanks for the camera, and we'll see y'all next time.